Imagine a world where robots don't just follow code but understand the laws of physics through intuition. We are witnessing the birth of physical AI, where large language models meet high-frequency motor control. This isn't just automation, it's the emergence of embodied intelligence. We're moving beyond pre-programmed paths into a realm of real-time reasoning and sensory feedback loops. The barrier between digital thought and physical action is dissolving right now, creating machines that perceive, reason, and act with human-like dexterity. For decades, robotics has been trapped in a paradigm of rigid programming. We used to write complex if-else statements to handle every possible edge case, but the real world is messy, unpredictable, and infinitely complex. A slight change in lighting, a shift in an object's position, or an unexpected obstacle can cause a traditional industrial robot to fail spectacularly. The sim-to-real gap remains the industry's greatest hurdle, where models trained in perfect digital simulations crumble when faced with real-world friction, gravity, and sensory noise. We've reached the limit of classical control theory and heuristic-based automation. We need a system that can generalize across tasks without needing a billion lines of manual code for every single new movement. The breakthrough came when we stopped treating robotics as a geometry problem and started treating it as a reasoning problem. By integrating vision-language action models, we can now feed raw sensoromotor data directly into transformer architectures. These models, often referred to as VLA models, leverage the vast knowledge of internet-scale datasets to understand semantic concepts like pick up the red cup and translate them directly into talk commands. We are using end-to-end neural networks that map visual pixels and proprioceptive states to continuous action spaces. This allows for zero-shot generalization, where a robot can perform a task it has never seen before simply by understanding the intent through its linguistic training. We're combining the high-level reasoning of LLMs with the low-level precision of reinforcement learning, creating a unified architecture that processes the world through a single, massive neural backbone capable of handling both logic and physics simultaneously. Building these systems requires a radical rethink of the hardware-software stack. At the core, we implement diffusion policies to handle the multimodal distribution of possible human actions, allowing the robot to generate smooth, probabilistic trajectories rather than jerky, deterministic paths. We feed high-frequency visual tokens from depth cameras and tactile sensors into a temporal transformer block. This block maintains a latent memory of the environment, ensuring temporal consistency in movement. To bridge the gap between simulation and reality, we utilize massively parallelized physics engines like Isaac Gym, performing millions of iterations in a fraction of a second. We implement domain randomization, varying friction coefficients, mass, and lighting during training to force the network to learn robust, invariant features. The control loop operates at sub-millisecond latency, integrating a low-level PD controller with a high-level neural policy. This hybrid approach ensures that while the transformer plans the intent, the classical controller maintains the stability and safety required for physical interaction with humans and delicate objects. The implications of this convergence are nothing short of revolutionary. We are moving toward a post-scarcity labor economy where humanoid robots can seamlessly integrate into domestic, medical, and manufacturing environments. This isn't just about replacing repetitive tasks, it's about augmenting human capability. Imagine a surgical assistant that understands anatomical nuances through visual reasoning, or a search and rescue drone that can navigate collapsed structures using semantic understanding. As the cost of compute drops and the density of sensor data increases, physical AI will become as ubiquitous as the smartphone. We are fundamentally rewriting the relationship between intelligence and matter, enabling a new generation of machines that can learn from experience, adapt to change, and operate autonomously in the chaotic complexity of the human world. Watch as this unit navigates a completely unstructured kitchen environment. Notice how it doesn't follow a preset path. Instead, it constantly re-evaluates its trajectory based on real-time visual feedback. It identifies a cluttered countertop, recognizes a specific tool, and calculates the optimal grasp pose using its onboard VLA model. As it reaches for the object, the tactile sensors detect the slippage, and the policy instantly adjusts the finger pressure to maintain a secure grip. There is no latency between perception and action. It handles the soft, deformable material of a cloth with the same precision it uses for rigid objects, demonstrating the incredible capability of learned deformation models. This isn't a scripted demonstration, this is a live inference of a neural policy responding to dynamic environmental shifts. The robot is thinking, feeling, and acting in a continuous, unified loop of physical intelligence that mimics the dexterity of a biological organism. The era of physical intelligence is just beginning, and the convergence of AI and robotics will define the next decade of human progress. Stay at the forefront of this technological revolution by keeping up with the latest breakthroughs in embodied AI. If you found this deep dive valuable, make sure to subscribe at Rahuldio 2047 for more technical insights. Link in bio for full code.